Intro. We often think of dinosaurs as Earth's greatest rulers. But what if I told you that before the dinosaurs, the planet was ruled by giant insects? During the Carboniferous period, soaring oxygen levels gave rise to bizarre creatures, like dragonflies with wingspans as wide as eagles. But how did this strange chapter of Earth's history come to be? And how did it end? To answer that, we need to go all the way back to the very beginning. The birth of Earth. Earth's story begins around 4.54 billion years ago, in a violent and chaotic corner of the cosmos. It was born from swirling clouds of dust and gas surrounding the young sun. Gravity pulled fragments of rock together, smashing them into a growing sphere. Each collision generated enormous heat, turning Earth into a molten world under constant bombardment by asteroids and comets. At this stage, Earth had no oceans, no clouds, just a fiery crust under a black, airless sky. One of the most dramatic moments in this early era was the formation of the Moon. Scientists believe a Mars-sized object named Theia collided with the young Earth. The impact was cataclysmic, blasting debris into space. Over time, this material coalesced into the Moon, which became Earth's permanent companion. That collision also tilted Earth's axis, giving rise to seasons even in its infancy. The Hadean Aeon, a hellish world. This brutal beginning is known as the Hadean Aeon, named after the Greek word Hades, a reference to its hellish conditions. As Earth cooled, its internal structure began to form. Heavy metals like iron sank inward, creating a dense core. Lighter materials rose to form the mantle and the planet's first thin, fragile crust. This internal layering would prove crucial. It set the stage for plate tectonics, volcanic activity, and the dynamic geology that continues to shape our planet. The arrival of water. Where did Earth's water come from? Many scientists believe it wasn't born here. Instead, icy comets and water-rich asteroids may have delivered water through repeated impacts. Over time, these celestial visitors brought enough to begin forming Earth's first oceans, though that future was still millions of years away. Earth's first defense, the magnetic field. Despite the violence, Earth was already developing a defense system, its magnetic field. Generated by molten iron in the core, this invisible shield protected the planet from the sun's deadly solar winds. Without it, Earth might have lost its atmosphere entirely, making life impossible. An alien world. Earth's surface remained an alien landscape. For millions of years, it may have been blanketed by a magma ocean, glowing rivers of lava flowing under skies filled with volcanic gases. There was no oxygen, only carbon dioxide, methane, and water vapor. Yet even in this inferno, change was underway. The crust cracked and shifted under immense pressure. Volcanic islands began to rise from the molten seas, hinting at the plate tectonics that would one day create continents and oceans. At this time, Earth spun at a dizzying speed. A day lasted just 6 hours. The seeds of life. Amid the destruction, the ingredients for life were being scattered across the planet. Carbon, hydrogen, nitrogen, delivered by asteroids and comets, were embedding themselves in the crust and atmosphere. Every fiery impact helped prepare the planet for the emergence of biology. This wasn't just chaos. It was a transformation. Earth was forging its identity, a planet with the potential for oceans, an atmosphere, and eventually life. Life begins the microbial age. Around 4 billion years ago, as Earth cooled from its fiery origins, something extraordinary began to unfold. With the emergence of liquid water, the essential ingredient for life, conditions were finally ripe, not for towering beasts or lush forests, but for something far simpler and more profound: microbes. These were prokaryotes, single-celled organisms with no nucleus. Though tiny, they were pioneers of life on Earth. They thrived in extreme environments where modern organisms couldn't survive. Far beneath the ocean's surface, hydrothermal vents spewed out chemical-rich water. And here, life took hold. These microbes didn't rely on sunlight. Instead, they used chemosynthesis, a process that allowed them to extract energy by breaking down compounds like hydrogen sulfide. This unique ability enabled them to colonize some of the harshest habitats on Earth: scalding vents, acidic hot springs, and deep-sea fissures. For billions of years, these microbes were the only life on the planet. But they weren't just surviving, they were changing Earth itself. The first architects of Earth. Among the oldest signs of life are stromatolites, layered rock formations built by colonies of microbes that trapped and bound sediments over time. These ancient biological structures still exist today in rare places like Shark Bay, Australia. Gazing at one is like looking billions of years into the past, at the handiwork of Earth's first engineers. Scientists believe that all life today may trace its lineage back to a common ancestor known as Luca, the last universal common ancestor. Luca wasn't a specific creature, but a theoretical microbe whose genetic code echoes through every living thing on Earth today. Though it left no fossil behind, its molecular fingerprint can be found in the DNA of every cell. The resilience of life. These ancient organisms were astonishingly resilient. Many lived without oxygen, sunlight, or organic nutrients, thriving in conditions that would be utterly lethal to humans. Their adaptability has even led scientists to theorize that similar forms of life could exist on other worlds, like Mars or Europa, where extreme conditions mirror early Earth. Despite their simplicity, microbes dominated Earth for an unimaginably long time. In fact, if Earth's 4.5 billion-year history were condensed into a 24-hour day, microbes would reign for nearly 20 hours. Humans, by comparison, would appear only in the last few seconds before midnight. While silent and unseen, these microorganisms were laying the foundation for all future life. They were cycling chemicals, reshaping the environment, and paving the way for a biological revolution. Oxygen and global ice ages. Then, around 2.4 billion years ago, a group of microbes changed the world forever. These were cyanobacteria, simple aquatic microbes that developed a powerful biochemical process, photosynthesis. They harness sunlight to convert water and carbon dioxide into energy, releasing oxygen as a byproduct. At first, this oxygen reacted with minerals in the ocean. But over time, it began to accumulate in the atmosphere. This slow shift triggered a planetary transformation known as the Great Oxidation Event, GOE. Before this, Earth's atmosphere had no oxygen, only methane, carbon dioxide, and other gases. The arrival of oxygen was revolutionary, but not everyone benefited. For much of Earth's life at the time, oxygen was toxic. Many anaerobic microbes either went extinct or were forced into isolated oxygen-free environments. The first snowball Earth. The oxygen didn't just impact life, it reshaped the climate. Oxygen reacted with methane, a potent greenhouse gas, drastically reducing its concentration. As a result, Earth's temperature plummeted, triggering a series of global ice ages. During these snowball Earth episodes, ice may have stretched from pole to equator. Even the oceans froze over, creating a white, reflective shell that bounced sunlight away. For millions of years, Earth became an icy wasteland. But eventually, volcanoes helped swing the balance. Eruptions released vast amounts of carbon dioxide, building up enough greenhouse effect to thaw the planet. As ice receded and oceans melted, Earth entered a new era, one in which complex life could evolve. The ozone layer and a new atmosphere. The oxygen released by cyanobacteria did more than change the climate. It laid the foundation for the ozone layer. In the upper atmosphere, oxygen molecules formed ozone, O3, which absorbed harmful ultraviolet radiation from the sun. For the first time, life could begin venturing into shallow waters and eventually onto land, without being scorched by solar radiation. Evidence of this ancient transformation is still visible today. Banded iron formations, layers of rust-colored rock, formed when free oxygen reacted with iron in the oceans. These ancient deposits are the fossilized proof of Earth's first large-scale environmental shift caused by microbes. In a way, this was Earth's first pollution event, one that painted the seas red and prepared the air for breath. The Ediacaran, the first animals. Around 635 million years ago, Earth began to thaw from one of the most extreme ice ages in its history. Entire continents had been buried beneath glaciers, and the planet was locked in a deep freeze. As the ice receded, a quiet but extraordinary era began, the Ediacaran period. This was a turning point in the history of life. For the first time, large multicellular organisms began to appear, a dramatic shift after billions of years of microscopic, single-cell dominance. These strange new life forms were the pioneers of complex biology, unlike anything we know today. Alien bodies in ancient seas. Ediacaran organisms were soft-bodied and surreal. Some resembled leafy fronds swaying on the ocean floor. Others were flat, ribbed discs, or puffed-up, quilted shapes like living pillows. They had no mouths, no eyes, no digestive systems, absorbing nutrients directly through their outer layers or filtering particles from the surrounding water. They lived in shallow, quiet seas, spread across ancient ocean beds and ecosystems that were still simple and low energy. There were no predators, no fast movement, no fight for survival as we know it. Life was just beginning to experiment with form, function, and complexity. This was evolution's first attempt at building a multicellular world, powered by oxygen, evolving slowly. By this time, oxygen levels in the atmosphere had risen just enough to support more complex life, but they were still far below modern levels. As a result, evolution in the Ediacaran period moved slowly and deliberately. Most organisms were immobile or sluggish, anchored to the seafloor, and tightly bound to their delicate environment. Still, this quiet stage was essential. It laid the groundwork for all that was to come. Fossils from a forgotten world. Fossils from the Ediacaran period offer rare and remarkable windows into this ancient time. These impressions, preserved in marine sediments, survived only because of extraordinary preservation conditions. Without bones or shells, the soft bodies of these organisms usually decayed quickly after death, making their fossils both fragile and incredibly valuable. Among the most famous is Dickinsonia, a flat, ribbed creature that could grow over a meter long. Giants, considering that life had been entirely microscopic just one geological period earlier. Yet, the true identity of many of these creatures remains a mystery. Were they early animals, fungi, or representatives of an entirely separate branch of life? One that left no living descendants? Evolutionary experiments. What makes the Ediacaran biota so fascinating is how alien they seem. Many have no modern relatives, no genetic fingerprints in today's living creatures. To some scientists, this suggests that the Ediacaran was a time of biological experimentation, a moment when evolution tested a variety of body plans and lifestyles, many of which were eventually abandoned. Entire branches of life may have emerged and vanished during this period, leaving only fossilized blueprints of forms that now seem otherworldly. They are biological whispers from a world long forgotten. A recent discovery in deep time. Surprisingly, the Ediacaran period was only formally added to the geological timescale in 2004, making it one of the most recently recognized chapters in Earth's history. Fossil discoveries in Canada, Australia, and Russia have helped expand our understanding, but many questions remain. Were these truly the first animals? Did they give rise to modern life? Or were they evolutionary dead ends? And why did most of them disappear so suddenly? The end of a quiet era. The Ediacaran didn't end in silence. It gave way to the Cambrian Explosion, a dramatic burst of evolutionary activity that introduced mobility, predators, and complex ecosystems. The calm, slow-moving world of the Ediacaran was replaced by a new one driven by survival and competition. Yet, the legacy of this period remains. The Ediacaran was the first time life stepped beyond a microscopic, the first attempt at building the kinds of organisms that would one day walk, swim, fly, and think. In the grand story of evolution, the Ediacaran was Earth's first rehearsal for the rich, dynamic diversity of life that would follow. The Ordovician period, life booms, then breaks. Spanning from about 485 to 443 million years ago, the Ordovician period was a time of spectacular expansion beneath the waves. Following the evolutionary surge of the Cambrian, marine life entered a golden age, diversifying, thriving, and evolving across Earth's oceans. This was a world teeming with strange beauty and biological innovation. Oceans of innovation. Life in the Ordovician seas flourished like never before. Corals began building the first true reefs, while brachiopods, clam-like creatures, anchored themselves to the seafloor in vast numbers. Mollusks, especially the formidable cephalopods, rose as apex predators, ruling the water with tentacled precision. Trilobites, those iconic survivors of the Cambrian, adapted to new ecological niches, continuing their reign as some of the era's most successful and diverse creatures. Among the evolutionary newcomers were the first vertebrates, jawless, armored fish known as ostracoderms. Slow-moving and primitive, these bony creatures were small but significant. Their protective exteriors represented early innovations in defense and survival. They marked the very first steps on a path that would eventually lead to fish, amphibians, reptiles, birds, and humans. Layered ecosystems and life's expansion. Ordovician oceans weren't just busy, they were complex. Food webs deepened, and species began to fill specialized roles within their environments. Reef-building organisms like corals and algae transformed the seafloor into vibrant underwater landscapes. Fueling this marine boom was intense underwater volcanic activity, which enriched the seas with nutrients. These nutrients spurred explosive growth in plankton, tiny organisms that formed the base of the food chain and supported vast marine ecosystems. Life's first steps on a land. While the oceans dominated, life was quietly making its first tentative move onto land. Fossils from this period show the appearance of early non-vascular plants, possibly resembling modern mosses or liverworts. These hardy pioneers clung to damp shorelines, surviving without roots or complex systems. Though small and simple, they were trailblazers, laying the foundation for the vast terrestrial ecosystems that would eventually blanket the planet. A world transformed and then undone. But this age of abundance would not last. Near the end of the Ordovician, Earth faced its first major mass extinction, the Ordovician-Silurian extinction event. In a span of just a few million years, 85% of marine species vanished. The likely cause, a sudden, intense ice age. A sharp drop in atmospheric carbon dioxide cooled the planet, triggering the rapid expansion of glaciers. As ice sheets grew, sea levels plummeted, shrinking the shallow marine habitats that had become cradles of biodiversity. Countless species, unable to adapt, were wiped out. And just as Earth began to thaw, a second blow followed. Melting glaciers caused sea levels to rise again, destabilizing ecosystems further. Recovery would take millions of years. Survivors and predators of the deep. Amid this upheaval, some life endured and adapted. Cephalopods, especially the giant nautiloids, cemented their status as the top predators of the Ordovician seas. With long, conical shells and tentacled arms, some grew over 6 meters in length, dominating the oceans like prehistoric great white sharks. Their fossils are striking remnants of a vibrant world, one teetering on the edge of destruction. Legacy of the Ordovician. The Ordovician period was a time of biological brilliance. It transformed Earth's oceans into rich, layered ecosystems and witnessed the first stirrings of life on land. But it also delivered a sobering reminder: no age of abundance is eternal. The mass extinction that ended the Ordovician reshaped the planet's evolutionary path, clearing the slate for new life to rise in the next chapter. Life moves to land, from the Silurian to the Devonian. Between 443 and 359 million years ago, Earth witnessed one of the most extraordinary chapters in its biological story, life's migration from water to land. This transition was neither swift nor easy. It was a slow, experimental journey, filled with failures, adaptations, and remarkable breakthroughs that would forever transform the planet. The first to venture ashore. The first life to leave the oceans wasn't animal. It was plant and fungal. During the Silurian period, simple green plants, similar to modern mosses and liverworts, began spreading across damp coastal environments. These pioneering plants were fragile, lacking roots or vascular tissue, but they could stabilize soil, trap moisture, and anchor themselves to the rocky surface, forming thin green mats along ancient shorelines. Alongside them came fungi, forming early symbiotic partnerships. Fungi helped break down rock and release vital minerals in exchange for nutrients from the plants. Together, they altered the land and the atmosphere, pulling carbon dioxide from the air and slowly contributing to a global cooling trend. This humble green carpet marked the foundation of Earth's first terrestrial ecosystems, the first animals on land. Soon after, the arthropods followed, millipede-like detritivores and early scorpion ancestors creeping across the early plant mats in search of food. Their tough exoskeletons helped retain moisture, while their jointed legs gave them mobility across dry terrain. By the late Silurian, more arthropods had begun exploring this new world, spurred on by rising oxygen levels that made breathing air possible. These small, scuttling pioneers laid the groundwork for future terrestrial animal life. The age of fishes, Devonian diversification. The Devonian period, often called the Age of Fishes, brought an explosion of diversity in the oceans. From tiny filter-feeding fish to massive predators, marine life reached unprecedented complexity. At the top of the food chain swam monsters like Dunkleosteus, a heavily armored, 10-meter-long fish with a crushing bite capable of slicing prey in a single motion. It was one of the earliest apex predators in Earth's history. Meanwhile, evolutionary innovations beneath the surface began paving the way for life on land. Lobe-finned fish evolved muscular fins supported by bone, structures strong enough to push along the seafloor or even briefly prop up in shallow water. These adaptations led to something extraordinary: the rise of tetrapods, four-limbed vertebrates that could one day walk on land. Tiktaalik, a transitional marvel. Among the most famous transitional species was Tiktaalik, part fish, part amphibian. Tiktaalik had fins with wrist-like bones, a mobile neck, and a flat crocodile-like skull. Though still aquatic, it could lift itself up and turn its head, early traits for life on land. Tiktaalik was a true evolutionary bridge, a creature testing the boundaries of two worlds. Forests rise, changing the planet. At the same time, plants were evolving too. Vascular plants emerged, equipped with internal plumbing to transport water and nutrients. This allowed them to grow taller, branching into the first forests. Giant plants like lycophytes and ferns began spreading across continents, creating shaded, nutrient-rich environments. These forests pumped out oxygen, reshaping Earth's atmosphere and preparing the way for more advanced life. The late Devonian extinction, a slow collapse. Around 375 to 359 million years ago, the Devonian's golden age came to a quiet, devastating end. Unlike sudden, cataclysmic extinctions, the late Devonian extinction unfolded slowly, a prolonged ecological crisis that dragged on for millions of years and wiped out nearly 75% of marine species. What triggered this collapse? A complex web of causes: massive volcanic eruptions, declining oxygen in the oceans, a condition called anoxia, and perhaps most significantly, the rise of land plants. These plants drew down carbon dioxide, cooling the planet. The cooler temperatures slowed ocean circulation, leading to stagnant, oxygen-poor waters, a death knell for countless marine organisms. The Kellwasser and Hengenberg events. The extinction wasn't a single event, but a series of deadly blows. The Kellwasser event devastated coral reefs and deep-sea communities, turning vibrant shallow seas into lifeless zones. Later, the Hindenburg event delivered the final strike, ending the dominance of ancient armored fishes and altering ocean life forever. Reef systems collapsed. Trilobite populations plummeted. Entire groups of species vanished, never to return. New life from the ashes. Yet, amid destruction came opportunity. As dominant marine species vanished, tetrapods, which had just begun their journey onto land, found new ecological niches waiting for them. Fewer aquatic predators and competition meant these early vertebrates could diversify and expand, slowly establishing themselves in terrestrial environments. The extinction cleared the evolutionary stage for land vertebrates to thrive. A world reimagined. Interestingly, fungi flourished in this disturbed world. With fewer plants and animals to compete with, strange organisms like prototaxites, towering fungal structures over 8 meters tall, may have briefly ruled the early land. And while speculative, some scientists have even proposed a gamma ray burst, a cosmic explosion, as a possible contributor to the extinction. If true, it would suggest that life's fate is not only shaped by Earth, but by the universe beyond. A new chapter begins. The Silurian and Devonian periods marked a pivotal turning point in the history of life. The conquest of land, the rise of forests, and the forging of the vertebrate body plan. Though the late Devonian extinction ended this era in devastation, it also marked the beginning of something greater, a reshaped planet teeming with new possibilities. From shallow waters to towering trees, and from crawling arthropods to lumbering tetrapods, the stage was set for the next great act in Earth's unfolding drama. The Permian, rise of the reptiles. The Permian period, lasting from about 299 to 252 million years ago, marked a major turning point in Earth's history. Following the lush, swampy environments of the Carboniferous, the Permian ushered in a much drier and more arid climate. This dramatic environmental shift reshaped ecosystems and forced life to adapt in bold new ways. A changing world. The vast wetlands that once blanketed the Earth began to disappear, replaced by expansive deserts and sparse forests. These tougher conditions gave an evolutionary edge to creatures that could survive far from water. Reptiles. Reptiles held one critical advantage over amphibians: the amniotic egg. Enclosed in a leathery or hard shell, it protected the developing embryo and allowed reproduction to occur entirely on land. No longer tethered to aquatic environments, reptiles began to spread rapidly, colonizing new and challenging terrains. The rise of synapsids. One of the most remarkable groups to emerge during the Permian was the synapsids. Though often mistaken for reptiles or even dinosaurs, synapsids followed a separate evolutionary path, one that would eventually lead to mammals. Among the most iconic synapsids was Dimetrodon, easily recognized by its large sail-like structure on its back. This sail likely played a role in thermoregulation, absorbing or releasing heat, depending on the temperature. Despite its reptilian appearance, Dimetrodon lived long before the first dinosaurs. In fact, it's closer in time to modern humans than to a T-Rex. Another notable herbivorous synapsid, Edaphosaurus, also had a sail on its back. Its exact function is still debated. It may have been used for mating displays, communication, or temperature control. Continental shifts and new flora. Meanwhile, Earth's land masses were merging into a single supercontinent called Pangaea. This massive formation created intense environmental extremes. Coastal regions remained relatively mild, but the vast interior turned into a parched wilderness, with searing daytime temperatures and freezing nights. Plants had to adapt too. The swamp-loving flora of earlier periods gave way to hardier, drought-resistant gymnosperms like conifers, which began to dominate the dry landscapes of Pangaea. Early mammal ancestors. Within the synapsid lineage, a group called therapsids began to show features we now associate with mammals. Some species exhibited semi-warm-blooded metabolisms, allowing more active lifestyles and internal temperature control. Fossil evidence even hints that some therapsids may have had whiskers or fur-like coverings. Early steps on the road to true mammals. Life in the oceans. Marine life during the Permian was facing its own set of challenges. While ocean biodiversity began to decline, several groups still thrived. Spiraled ammonites continued to flourish, and early sharks prowled the seas. But overall, the oceans were becoming more unstable due to fluctuating temperatures and oxygen levels, a sign of the catastrophe to come. The Great Permian Extinction, the Great Dying. Around 252 million years ago, the Earth experienced its most catastrophic mass extinction, known as the Great Permian Extinction, or simply the Great Dying. This event wiped out approximately 90 to 96% of marine species and about 70% of land-dwelling vertebrates, making it the most severe extinction in Earth's history. A planet in crisis. The crisis is believed to have begun with massive volcanic eruptions in what is now Siberia, forming the vast Siberian traps. These eruptions released colossal amounts of carbon dioxide, CO2, and methane, triggering an extreme greenhouse effect. Global temperatures soared. In some areas, especially near the equator, temperatures may have surpassed 50 degrees Celsius, 122 degrees Fahrenheit, lethal for most life forms. Oceans turned deadly. The oceans bore the brunt of the atmospheric changes. CO2 dissolved into seawater, leading to acidification, which destroyed coral reefs and weakened the shells of marine organisms. Oxygen levels plummeted, creating vast dead zones in the seas. In these stagnant, oxygen-depleted waters, hydrogen sulfide gas, a highly toxic substance, began to build up. This poisonous gas may have seeped into the atmosphere, further worsening air quality and contributing to the collapse of both marine and terrestrial ecosystems. Collapse of life on land. Life on land fared little better. Food chains disintegrated, and many dominant species, including most large therapsids, perished. Insects, which had once flourished in carboniferous swamps, suffered massive losses. Yet some creatures managed to endure. Lystrosaurus, a stout, burrowing therapsid, was among the few land animals to survive. Its ability to dig and perhaps tolerate harsh conditions may have been key to its survival. These resilient survivors formed the foundation for the long recovery ahead. A world of decay. As ecosystems collapsed, fungi surged in abundance. Fossil records show a marked increase in fungal activity, a phenomenon known as the fungal spike. With so much dead organic material available, fungi thrived, dominating a world trying to recover. For a brief time, Earth became a planet of rot and decay, a haunting reminder of the fragility of life. A devastating reset, a new beginning. The Great Permian Extinction was not just an end. It was also a brutal reset. Entire evolutionary lineages were wiped out, including many trilobites and large synapsids. But with so many ecological niches suddenly vacant, new opportunities emerged. The survivors, including early reptiles and mammal-like therapsids, would go on to shape the next era. Their persistence laid the groundwork for the rise of dinosaurs, mammals, and eventually modern ecosystems. Despite its horror, the Permian's end was a pivotal moment in Earth's story, one that proved life's incredible capacity for adaptation and recovery in the face of overwhelming catastrophe. The Pleistocene, humans, and megafauna. Spanning from about 2.6 million to 11,700 years ago, the Pleistocene epoch was a time of extremes, a relentless dance between glaciation and thaw. Vast ice sheets advanced and retreated across the continents, carving valleys, reshaping landscapes, and transforming ecosystems with every surge. But ice wasn't the only giant of the age. This era teemed with massive creatures, megafauna, that pushed the limits of evolutionary imagination. Mammoths with spiraled tusks and thick shaggy coats roamed the frozen tundras. Saber-toothed predators like Smilodon stalked their prey through the cold. Towering ground sloths lumbered through ancient forests, and armored glyptodons, as large as compact cars, moved beneath domed, turtle-like shells. Early human species, from Homo habilis to Homo erectus, began to shape their world using tools, fire, and social cooperation. As Homo sapiens emerged, they demonstrated an extraordinary ability to adapt, not through fur or fat, but through innovation. They clothed themselves in hides, crafted tools to hunt and survive, and mastered fire for warmth, cooking, and protection. Humans weren't alone. Other hominin species like Neanderthals in Europe and the elusive Denisovans in Asia shared the Pleistocene world. Genetic evidence reveals that interbreeding between these groups occurred, leaving traces of their DNA in modern human populations. Yet humans weren't the only ones adapting. Megafauna, too, evolved in response to the cold. Mammoths grew denser coats and adapted behaviors to survive deep winters. Woolly rhinos used strong horns to dig through snow in search of grass. Many large animals developed migratory patterns, following the changing seasons in search of food and more hospitable climates. Around 20,000 years ago, the last ice age reached its peak. Towering glaciers, nearly 2 miles thick in some places, blanketed North America, Europe, and parts of Asia. Sea levels dropped, exposing land bridges like Beringia, which connected Siberia and Alaska. These temporary paths enabled the movement of animals and humans. It's through Beringia that humans likely first entered the Americas, continuing a global migration that would span every continent except Antarctica. As the planet warmed and the ice sheets retreated, the Pleistocene came to a quiet but dramatic close. The warming climate transformed landscapes and ecosystems. Ice Age grasslands gave way to forests and wetlands. Many megafaunal species, creatures that had dominated the frozen earth, vanished. Why these extinctions occurred remains a topic of debate. Rapid climate change likely disrupted food sources and habitats. At the same time, increasingly organized human hunters, armed with spears, strategies, and cooperation, targeted large animals for food and materials. On continents like Australia and the Americas, where megafauna had no prior experience with human predators, extinction came swiftly. The end of the Ice Age and the dawn of civilization. About 11,700 years ago, Earth transitioned into the Holocene epoch, a time of warming and stability. The relentless glacial cycles ended, ushering in a new chapter in both climate and culture. As glaciers melted, they poured vast amounts of fresh water into the oceans, raising sea levels and drowning ancient coastlines and land bridges like Beringia. Entire regions were reshaped, isolating populations and creating new geographic boundaries. This environmental shift laid the groundwork for a fundamental change in human behavior, settlement. With warming climates came biodiversity booms. Cold plains once home to mammoths and woolly rhinos gave way to lush forests, rivers, and fertile grasslands. Humans began to recognize the potential of these ecosystems, not just for hunting, but for cultivation. Early societies identified wild plants like wheat, barley, rice, and maize as reliable food sources. Over generations, they domesticated crops, selecting the most productive strains. Agriculture was born, enabling food surpluses and more permanent communities. Domestication didn't stop with plants. Animals like goats, pigs, sheep, and cattle became integrated into daily life, providing food, labor, and materials. Interestingly, dogs may have been the first species humans domesticated over 15,000 years ago, long before farming began. These early partnerships, based on hunting and companionship, laid the groundwork for today's human-animal relationships. The shift to farming led to monumental societal changes. With more stable food sources, populations grew. Villages became towns, and eventually, the first civilizations emerged. In the Fertile Crescent, humans built cities, developed writing systems, and established trade. Similar developments occurred independently across the world. In China's Yangtze Valley, India's Indus Valley, the Nile River region, and Mesoamerica, each shaped by local environments and innovations. Maize became central in the Americas, while rice thrived in Asia. The predictability of the Holocene climate allowed people to track the seasons, create calendars, and plan agricultural cycles. Irrigation systems were developed to manage water, and early astronomy emerged from watching the stars. These systems supported massive cultural achievements, from monumental buildings to rich spiritual traditions. One of the most mysterious early sites is Göbekli Tepe in modern-day Turkey. Built over 11,000 years ago, before agriculture, it features massive carved stone pillars. Its existence challenges traditional assumptions that farming came first, suggesting that spiritual or communal gathering may have preceded sedentary agriculture. But civilization came at a cost. Forests were cleared, rivers were redirected, some wild animals were hunted into extinction. For the first time in Earth's history, a single species, humans, began reshaping the environment on a global scale. These early civilizations laid the foundations for the modern world. From the first wheat fields to the first written words, the Holocene marked the transformation of humanity from nomads into the builders of complex societies. A new chapter. Earth's history is a saga of survival, transformation, and rebirth. Every extinction paved the way for new life. From small mammals in the age of dinosaurs to us, life always finds a way forward. As we face our own challenges, climate change, extinction, environmental instability, we must remember the lessons of the past. Because the next chapter of Earth's story is being written right now.